No, 3. So approximations to roots, because of course not all equations are easy to solve. And so we want a technique that will allow us to approximate the solution. And depending on how accurate we want it, we might only want it to 1 decimal place, and so it'll be reasonably easy to estimate. The first idea is a very basic idea called halving the interval. So if we've got some random function and it's continuous, the key is obviously it has to be continuous between 2 points and they're opposite in sign. So function A gives me a positive number here, function B gives me a negative number. Because the curve is continuous, there must be a solution in between A and B. Okay. So the trick is, let's find it. Well, halving the interval, as the name suggests, is, well, as an estimate, we'll go halfway between A and B and see what happens. Okay. So let's use this as an example. X to the power of 4 plus 2x minus 19 equals 0. And we know that there is a solution between 1 and 3, because function 1 turns out to be, where is it? Function 1 turns out to be negative. Function 3 turns out to be positive. It is a polynomial, so we know it's continuous. So the solution is in there somewhere, but where? So we'll average them out. Average of 1 and 3 is 2. Function 2 turns out to be 1, so obviously it's not the solution. But what I now know is I can trap it in a different interval, because function 2 is positive. Function 1 is negative, so I now know the solution must be between 1 and 2. So this sort of thing, I can say, well, okay, I knew function 3 is positive, function 2 turned out to be positive. So now, instead of going between 1 and 3, I know the solution is somewhere between 1 and 2. And so I can halve that interval. And so try 1.5. And that is a negative answer, negative 10.9. So now I know that the solution, well, 1.5 turned out to be negative, so it must be between 1.5 and 2. So I can halve that interval. The average of that is 1.75. It turns out to be negative. So again, I could go, okay, well now I know 1.75 is negative, so the solution must be between 1.75 and 2. So I'll average those ones. And I get 1.88. And that turns out to be negative. So okay, 1.88 is negative. So I now know the solution is in between 1.88 and 2. So I can average those two out and get 1.94. That turns out to be a negative value. So now, okay, well, it's in between 1.94 and 2. So I can average those two out and I get 1.97. Now just because the solution is 0.0001 doesn't necessarily mean I'm close to the answer, because a graph could do a funny thing. It might be 0.001, but then all of a sudden the graph might go up a mile. So don't assume that that's going to be the answer because we're so close. Yes, it is 0. The answer is 0 to 2 decimal places, but that's not what we're looking for. We want the actual number that we're substituting in to be accurate to 2 decimal places. So all right, 1.97. We now know the solution is in between 1.94 and 1.97. Average those two out, and I get 1.96. That's negative. Okay. So I now know it's between 1.96 and 1.97. Well, which is it then? Because remember, we want it to 2 decimal places. So it's either going to be 1.96. It's where it cuts is either going to be closer to 1.96 or closer to 1.97. Which one? Well, if I halve the interval again and find out where the middle is, 1.965, go to 3 decimal places, 1.965 turns out to be negative. Therefore, my solution must be closer to 1.97 than it is 1.96. So 1.97 is going to be my approximation to 2 decimal places. Now, don't panic. In a test, they're not going to ask you to keep going and keep going and keep going and keep going like that. They usually just ask you to, apply the idea once or twice to come up with a better approximation so that they can see you know how to use the idea. Obviously, this sort of technique lends itself very nicely to spreadsheets and things like that, where you can just copy the formula down and bang, 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 you'll find it very quickly. Well, that's a nice method. It's a very logical method, but there's a quicker way of doing it, thanks to our good old friend Newton. So many things we do because of Newton. His method, actually, there is a rumour around that it wasn't Newton. Someone else came up with it first, and Newton just stole the idea. No. Yes, that's why sometimes you'll see it called not just Newton's method, try to think of the other fellow's name, Rapson Newton or something like that. So some people give the other bloke some credit as well. Yes, scandal, back in a few hundred years ago. So, now, a few things to use Newton's method, or the supposed Newton's method. X0, so our first approximation, needs to be a pretty good approximation for it to work, because you can have bad approximations and it means Newton's method just fails. It's hopeless. But what it basically does is it finds where the tangent cuts the x-axis. So you've got some sort of curve. And say I want to find this solution here, the first one there, that x-intercept. And I estimate it by x0. So what the formula does is it finds where the tangent at x0 cuts the x-axis. So theoretically, that should get closer. If I put x0 in the right spot, the tangent should then get closer to the solution. That's what I mean. There are bad places. If I was trying to find this solution and I put it on the other side of the turning point, well, the tangent's going to go to the wrong solution. So that would be a bad first approximation. If it was a stationary point, that's what we'd call a hopeless one, because it's going to be parallel to the x-axis. It'll never cut it, so that Newton's method would fail altogether. Okay. So there we go. So that's what I was just saying. If it turns out to be a stationary point we try, then it's just not going to work. Okay. So use the tangent to find x1. Here's how he came up with the formula. The slope of the tangent, of course, is function x0 minus 0 over x0 minus x1, because obviously the y value at x1 is 0. So the derivative at x0 is equal to function x0 minus 0, because slope of the tangent we know is the derivative at x0. Rearranging that and arranging it a bit more, if x0 is a good first approximation, then we simply use this formula. So it's a rearrangement of it. x1 is going to be our next guess. It'll be our first guess minus function x0, so what we get when we put it in, divided by the slope of the tangent at that point. So the derivative is on the bottom. A lot of people make the mistake of putting the derivative on top rather than the bottom. But remember, it must be the derivative on the bottom, because remember, stationary points fail. Why does it fail? Because the derivative is 0. You can't have 0 on the bottom of the fraction. So the derivative must go on the bottom of the fraction. And you keep going, depending again on how accurate you want your approximation to be. So there's a generalization of it. xn plus 1 will be xn minus function xn over f dash xn. Same question. Okay, now I know we've got our approximation. Let's pretend we don't know what it is. Okay, we've got to pick a good first approximation. There's my function. I'm going to need my derivative, 4x cubed plus 2. My first approximation is going to be 1.5. Okay, so we originally said it was between 1 and 3. I've narrowed it down a bit and said, well, because our next one went there, so right, it's between 1 and 2. So all right, 1.5 is my first approximation. Well, function 1.5 is minus 10 point, etc. Sub it into the derivative, I get 15.5. Let's plug it into our formula. So the first approximation minus the value when we sub it in over the derivative, and I get 2.21 as my next approximation. Now, remember our answer was, what was it, 1.97? So it looks like it's shot away. Well, all it means is it's now on the other side of the solution. It actually is closer, I think. Is it? Yes, it is. All right, so we'll try it again. There's function 2.21 and its derivative. Sub that one in, I now get 2. And so again, I've got a bit closer to what we know the answer to be, 1.97. Okay, function 2 is 1, its derivative is 35. Sub it in again, we get 1.97. Okay, now we know that's the answer, but let's pretend we don't. So, all right, let's keep going. 1.97.001 over the derivative, that should tell me I am close. Not just because that's very close to 0, but the slope is quite large. So if I'm subtracting the fraction with something very tiny on top, something very large on bottom, I'm subtracting a very small amount. And to 2 decimal places, it turns out to be 1.97. So clearly, if I just keep going, I'm just going to keep getting 1.97 and 1.97. So 1.97 is my better approximation. So it only took 4 applications to get there this time. Had I picked 2, which I should have done when you think about it, because we knew it was in between 1 and 3, if I'd chosen 2 as my first approximation, I would have gone straight there, 1.97. All right, we can use Newton's method to approximate things like square roots. Okay? All we have to do is come up with an equation which would have the square root of 23 as the answer. And then if we know that, then we know the solution to that equation will be an approximation to the square root of 23. So I suppose the most logical equation would be x squared minus 23 equals 0. Okay? Has to be something equals 0. So you move all the terms to one side. So function x will be x squared minus 23. My derivative will be 2x. Another way of doing it is to just create a formula. So rather than sub the numbers in, sub the actual derivative in to create a formula. And so I've got, well, xn will be xn minus 1 minus xn minus 1 squared minus 23 over 2 lots of, which I've then made one fraction, and then just sub into that formula. It's just an alternative way of handling Newton's method. So, okay, well, 5 I know is the square root of 25. So I figure square root of 23 has got to be pretty close to the square root of 25. So if I sub 5 in, 5 squared plus 23 over 2 times 5, I get 4.8. We want the answer correct to 2 decimal places. Sub 4.8 in, I get 4.7958333333333333, which of course to 2 decimal places is 4.8. So I'm there straight away. So it looks like my approximation to 2 decimal places of the square root of 23 is 4.80. Okay, go on, someone see how good it is. Find the square root of 23. Is that a good approximation to 2 decimal places of the square root of 23? Yes. Yes, works? There you go. So the trick is you want to come up with an equation which would give you the answer. So I had to come up with an equation that would give me the square root of 23 as the answer. It doesn't say, simplest one is x squared equals 23, but moving everything to one side, the function becomes x squared minus 23. Some other problems that might occur with Newton's method. Approximations oscillating. So let me show you this example. Here's a random curve. Say I wanted to find that first root there. And as an approximation, I took x1 there. So x2 will end up there. All right. Oh. So you see what's going to happen. My tangent then went through x1. So x1 is my next approximation. Well, that tangent will go through x2, and I'll just keep going around in circles and circles and circles. So if that does happen, you might just want to change your x1 slightly. Unfortunately, you've picked one that sent yourself into a loop. As I mentioned before, if you pick on the wrong side of the stationary point, it's going to converge towards the wrong solution. So not necessarily the one you're looking for. So if I wanted to find the first solution there, but I picked one on the other side of the turning point, the tangent's going to end up over at x2, and I'll probably end up finding. Depending on the slope of the graph, though, it is possible I might end up back there, but it would be unusual. Okay, 6E.